This section is about slope fields. Slope fields are a tool that you can use to estimate solutions to differential equations without actually solving a differential equation. You can use a slope field to sketch what a graph of a differential equation is, and sometimes from that graph you can figure out what the differential equation is. What the solution is. So here's a differential equation. It's dy dx is equal to x plus 1. And what the differential equation tells us is the slope of the curve at any given point. So if I know the x-coordinate and the y-coordinate, I should be able to figure out the slope of the curve. And some questions that are helpful to ask yourself as you're sketching a slope field, it is sometimes helpful to figure out where would the slopes be equal to 0. So you can set your differential equation equal to 0, and the slopes are going to be equal to 0 for this differential equation if x is equal to -1. So that means anytime my x-coordinate is -1, I can draw a little horizontal line segment because my slope is going to be 0 for those points. Where are the slopes undefined? So that would be another important question to ask ourselves. But for this particular differential equation, because it's just x plus 1, there aren't any places where the slopes are undefined. And then what patterns can we find to help us save time? What I notice about this differential equation is that there are no y's in it. So really all that matters is what the x-coordinate is. So as I'm making a list of points, I could try 0, 0, and then I know the slope would be, well, the x-coordinate plus 1, so the slope would be 1. And so I'm going to sketch a short line segment here with a slope of 1. I'm aiming at this dot at the dot up 1 over 1 as I'm sketching that short line segment. And I could add another row to my table that says 0, 1, but I know the slope will still be 1, so it's going to save us some time just to realize that as long as the x-coordinate is 0, our slope is 1. And then we can do the same thing for if our x-coordinate is 1 and I don't really care what the y-coordinate is, then the slope would be 2. Now I'm aiming at a dot that is up 1 over 2 from where my point is, or down 1 over 2. So when I'm here, I was actually aiming down at the dot at 0, -1. All right, so if my x-coordinate is 2, I don't care what the y-coordinate is, my slope would be 3, so I'm going to draw line segments with a slope of 3, and after we get to a slope of about 3, they basically start looking vertical, but if my x-coordinate is 3, my slope would be 4, and so I'm drawing line segments with a slope of 4 here. And then I don't have all of these dots covered, so I could say, well, if my x-coordinate is -2, I don't care what my y-coordinate is, my slope would be -1. And so now I'm going to have a downhill slope for this parallel line, that vertical line. And at -3, don't care what the y-coordinate is, my slope is going to be -2. And so I don't know if you can tell, but this looks a little bit like a parabola. So if I start here, my parabola is going to curve upward, So it's a parabola shape, which kind of makes sense because this is actually an antiderivative that we can figure out what it is. So we could do this one. We can't always do them. And remember, an antiderivative would have a plus c on it. So this is a whole bunch of parallel parabolas if we sketch those through the slope field, which is why we would need to have a starting point in order to figure out what the exact equation for this parabola is. But we can tell by looking at it that it's definitely a parabola. All right. So here's another example. We have the differential equation dy dx is equal to -y over x, and we want to ask ourselves where would the slopes be equal to 0. So 0 equals -y over x. I don't care what x is, this would be equal to 0 when the numerator is equal to 0 or when y is equal to 0. So I don't care what x is, but if y is equal to 0, my slope is going to be 0. And so that means all along here, where my y-coordinate is 0, I'm going to have horizontal line segments. But I actually should have talked about the origin. At the origin, I have 0 divided by 0, which doesn't make any sense, so I'm not going to fill in a line segment for that point. Where are the slopes undefined? Well, the slopes would be undefined because it's negative y over x. That does not exist if x is equal to 0. So in my table, if x is equal to 0, my slope is going to be undefined. So those are going to be little vertical line segments when x is equal to 0. And then I would do some points. So let's say x is 1 and y is 1. So at this point, we're going to have a slope of negative 1. And actually, that's also true if x is negative 1 and if y is negative 1, because those would both be the same side. So we'd have a slope of negative 1 here and here as well. If x is negative 1 but y is positive 1, then we would have a slope of positive 1. And same thing down here. And also, that's true on this whole diagonal, right? So this would have a slope of 1, and this would have a slope of negative 1, and this would have a slope of 1, and this would have a slope of negative 1. You don't have to fill in the table, but you may fill in the table for as many points as it's helpful for you to see. So then let's say I'm going to try to figure out this point here. That ordered pair would be 2, 1. And so if I'm at 2, 1, my slope would be negative 1/2. And so negative 1/2 would be downhill, and I'm going to aim at this point up here. So that point would be negative 1/2. This one would be positive 1/2. This one would be negative 1/2. And this one would be positive 1/2. And I would do the same as I'm going through. I would try to figure out all of my ordered pairs. So this one is 3, 1, and so that would be negative 1/3. And then I would point at a point where that would work for it. This point would have a slope of negative 2/1. And so I don't know about you, but I'm starting to see that this slope field looks like it would graph the hyperbola function. Looks like it would graph kind of that 1/x, right? All right. So that would be sketching a slope field. The other thing you might be asked to do in these sections is reasoning using a slope field. So maybe sketching what a solution would look like. And so I'm going to start here at 5, 1, and I'm going to let the slope field guide me. So I have a slope here that's getting steeper and steeper the further out I go. So steeper and steeper. And then I have one, and then here it's getting less steep. So I'm going to follow those slopes, allowing it to get less steep. And then it's horizontal here. And then it's going to start slanting downward, but it's not going to cross this asymptote. So it looks something like this, my solution to that curve. Okay, it's not going to be perfect. I'm not a machine, but I should be able to say, yeah, it's about this slope here. It's about horizontal here. Like I should be able to see that it's following the guidance of the slope field. Now, what I just graphed here is not the differential equation. What I just graphed there would be the solution to the differential equation. I don't know what the equation for that solution is, but I do at least have a picture of what the graph is. In order to have a solution to a differential equation, you need two things. You need the differential equation, and then you also need a starting point. Then this question says there's one solution to the differential equation that is a linear function. What is the equation for that line? And when I started at 5, 1, it was not a straight line. But if I had started up here at 5, 6, then I would be along my asymptote. I would actually be on the asymptote, so I would have a linear function there. And so the equation for that linear function would be y is equal to x plus 1. And then this says verify that that is a solution. So let's go ahead and do dy dx is equal to 1. And is 1 equal to y minus x? Yes, it is, because if I solve this for 1, I get y minus x. So that is kind of a justification that, yeah, that is the solution that works. All right. Here is a slope field for a certain differential equation, and which of the following could be a particular solution. And so you kind of have to know, okay, well, this is not a parabola because these slopes are not going to point me towards a parabola. It's not e to the x because e to the x should be about flat here. So that doesn't match what e to the x looks like. E to the negative x looks like that. So no, it's not, doesn't look like that either. Cosine of x would start at 1 and be flat and then do this. That's not what those slopes are telling me to do. But natural log of x, I'm going to erase all my writing. Natural log of x starts out, has a vertical asymptote, and then curves up. So yeah, it kind of looks like natural log of x, although I didn't follow it very well. But that's the one that it looks like the most. I'm going to try following that a little better. So it's pretty vertical, getting less steep, getting less steep, getting less steep, getting less steep. It's almost done, Isla. And so that looks like the natural log function. And I followed the slope field pretty well. So just to emphasize, the graph that I graphed in green is the solution. The little line segments I would create by knowing the differential equation. All right, that is slope fields.